yesterday's lecture, which is still about shear and the stresses induced because of shear. Okay. So yesterday, just to remind you, yesterday we talked about specifically about stress evaluation, how we estimate the stress at different location along the depth of the section. Okay. So yesterday was about how could we evaluate shear stresses at different location along the depth of the section. Today is about shear flow. So we need to know how to estimate shear flow. As I told you that it's not just about the transverse shear stress, we also have longitudinal shear stress. What longitudinal shear stress causes is that when you have like a beam made up of three layers, you could say, three planks of wood laid on top of each other. When you apply a force due to shear flow, especially if these planks are not bonded to each other, these three planks would extend out from both sides. Okay, from both sides, and that is caused by the longitudinal shear stresses. That is caused by the longitudinal shear stresses. That is why it's important for us to be able to evaluate shear flow so that we could design screws or rivets or fasteners to connect these layers of planks or wood or whatever the material is made of, so that they don't slide relative to each other when you apply a force. They don't slide relative to each other when you apply a force. And you could see we have examples. So if you have like this T cross section and it's not made up of a single component, that means you have this component is glued or fastened to this component, and this component is glued and fastened to this, and the web is fastened and glued to the flange. So at that point, shear flow is important. Shear flow would be important. We have examples. I let you see. The easiest one is this one. You see that this I-beam is made up of how many components? One on top, one on bottom, and the web. So the flanges the flange at the top is not connected, it's not a single unit with the web. So it's a component, an independent component. So it has to be either glued or fastened using a rivet or a screw or whatever you want to use. Okay, so shear flow, if you have like no screw and you apply a force on this I-beam, then this upper side, or the flange, sorry, would have this relative motion, and it would get disintegrated from the web. The same thing goes to the bottom side, which is the flange. The flange, again, if you apply a force, then it would also have this relative motion that would get it disintegrated from the web, because they are components. They are not a single unit. This one is not part of this. The flange is not part of this web, and the same thing, the bottom side is not part of the web. So they are fastened. They are using a rivet or a screw, or maybe sometimes we use glue. So shear flow, so to estimate shear flow, that would enable us to know how much of rivets or screws we could place, or how much of what would be the spacing between the screws if we know about their shear strength. So that is the importance of knowing about shear flow. Okay, this is how important a shear flow is. You could see over here also we have two pieces connected to each other. If there were no connection, then when you apply a force, there would be some relative displacement between the top side and the bottom side. because of what? Because of the the longitudinal shear stress. Okay, and I explained to you yesterday on how the transverse shear stress would cause these independent components to have relative displacement, right? So we go now on how we could evaluate. So shear flow and built-up members, those are built-up members. We call them built-up members because they are composed of few components. Okay, it's not a single. This T is not a single unit. It's not like you cast in you cast in concrete and you come up with a single unit of T shape. Okay, so you have components fastened or glued to each other. So these sections, we call them built-up members or built-up sections and so on. Okay, shear flow is indicated to as Q. Shear flow is indicated to as Q. How can we evaluate shear flow? If you look at the formula, it looks like exactly the same as the shear stress, tau. The only difference is that with tau, we have VQ over I times T. If you still remember, tau's formula is V times Q over moment of inertia times T. If you look at this formula, what is missing is the T. What is missing from the tau formula is the T. So the only difference is that we don't have the variable T, that which would reflect the thickness of the member at which the section is taken, and tau ought to be evaluated. But over here, we could evaluate shear flow using this formula. Now we need to learn about the mechanism on how we apply this formula to calculate shear flow. We need to understand the mechanism with which we could apply this formula to get shear flow. So the same thing, I don't need to define again what V is and what I is and what Q is, because the same thing that we had in the tau or the shear stress formula, the same thing is V is the internal shear force, I is moment of inertia about the neutral axis of the composite shape if the shape looks like this, and Q is the moment of area, you could say, of the cross section of the cross of the part that the section, how to say that, is the moment. If you take a section over here, so it would be the, okay, we solved the example, then we could see what Q is. Okay, I don't need to define it. You could see it visually. Okay, now we have, this is our first example. This is a built-up members. This is a built-up members. Why? Because if you see that how many components we have, 1, 2, 3, 4. 4 components. We have 4 components. So we need to know on how to apply the formula for solving this problem. Let us see what the question is asking us to do. The beam is constructed from 4 boards glued together. They are glued, and we could see the points at which the components are glued to each other. These are the points at which the components are connected to each other or glued to each other to act as a single unit. If it is subjected to a shear force, so we have a shear force. We have a shear force, and the value for the shear force is given. And you could look at the cross section. The shear force is acting downward. Okay, 850 kilonewton is the shear force. Determine the shear flow. Determine the shear flow at B. It's specified where to take the shear flow, and C. So it seems that we have points at B and C. Let us look. Yes, B is here and C is here. Okay, that must be resisted by the glue. So it seems that we have glue at these points, and of course the other side as well. So what is the question is asking us to estimate the shear flow for these 2 points, B and C. Okay. So now we go and solve the question. Now we go and solve the question. So let us see. Let us see. So as you could see, I let you, now I explain to you. Now you don't need to worry about how we find, because you can't solve it. You haven't covered the topic of centroid for composite shapes and moment of inertia. So if you still remember the formula, we need to know that we can, the formula for shear flow is Q, shear flow is equal to Q, V times Q over moment of inertia. So because of this moment of inertia, we need to know about the location of the neutral axis. That means the centroid for the composite shape, and we need to calculate moment of inertia, okay, because of this. A Q is, the unit of Q is always either kilonewton per meter or Newton per millimeter, okay, Newton per millimeter. So shear force is in kilonewton, we converted into Newton. Q is, as yesterday, is millimeter cube, okay, millimeter cube. So this is the formula. So as I told you, we don't need to worry about this. Later on, I will cover it for you on how to calculate the centroid and moment of inertia of such a composite shape. You need to know on how to calculate these things, okay? The centroid and the moment of inertia of such a composite shape. So now what we have what we need that to solve the problem, what do we need to have? What do we need to have? V, do we have it? Yes, so I have V. What is left is only Q. What is left is only Q. So now we come and see what we need to, what is the mechanism through which we could calculate Q. If you look at this section, okay, if you look at, sorry, at this point, that means we need to have a knife, okay, have a knife. Why do we need to have a knife? Because I need to cut, to have a sec, to cut this composite shape or built-up member. I need to cut it at this location, okay? So when I cut this member at this location, the mechanism is this. You have a mirror, okay, at where to place the mirror, exactly at the center of the shape. We place a mirror, okay? We place a mirror, okay? We place a mirror, okay? This is mirror. Okay, we have a mirror at the exactly half of the shape, okay, so symmetrical. So you could see what do we have of components or elements on the left side? We have the same on the right side, okay. So now when I have a knife, okay, I draw it for you so that you don't remember, you don't forget. We have a knife, okay, this is the handle, okay, we have a knife. I come and cut I take a section, that means I cut it at point B, okay. The mirror would do the same thing. What I did over this side, I need to do it on the other side. What I did on this side has to be done on the other side, okay. So this will be automatically cut. So which part of the composite of the built-up member would fall? Which part of it would fall? Do we have any, after cutting B at this at the left and the right, would there be any component that would fall? Would there be any component that would fall? This is my knife. I cut on B. Okay, this is my knife. I cut at B, and the mirror did the same thing to the other side. Okay, so is there anything that would fall? Is there anything that would fall? Nobody?
أي بمكان أوانينا عمص في كسنينا بمكان بمخوارة لون من أو the left one
okay.
isn't like
Okay. No, it's not. This is, I'm not talking about the, this beam is a built-up beam. So you have, these are components, or these are boards connected to each other. One board, second, third, fourth, glued to each other at this point, this point, this point, this point, okay? So my question is, which part if I cut the beam at this point and the mirror would do the same at this point, would there be a part from the beam, from the built-up member that would fall or would get disintegrated? Not to, let us say disintegrated, not fall, because I know what you think now. You think that this part, the whole three components would fall apart from the top, which is true. But this would be disintegrated from the original section. This part, the above one, okay, the one on top, or the so-called flange, would get disintegrated, would get disconnected, let's say, would get disconnected from the rest of the section. Do we agree on that? If we cut it at B and the mirror would cut the opposite side of the point at which the member is connected to the rest of the beam, do you agree that this part would get disconnected if I cut it at these 2 points? Yes or no? It's clear enough to know that yes, this part would get disconnected, right? Because it's glued at these 2 points, right? It's glued. Is it difficult to imagine that if I cut it at this point and this point, the top side or the flange side of the member would fall or would get disconnected from the rest of the section? Is it difficult to imagine it?
أستاذ disconnect دي بديارة.
It gets disconnected. So I was waiting for someone to tell me that it would get disconnected. So now we've got it disconnected. Just now I told you the mechanism with which to estimate Q is very much important. What I meant by the mechanism. Now for the Q, we have to write the equation V times Q over moment of inertia, okay? So moment of inertia, we don't need to have a mechanism to understand. Just you have formulas, you have how to transfer the moment of inertia about its centroidal axis to moment of inertia about the neutral axis of the composite shape. That's all what you need to know about when you deal with moment of inertia. V, if you don't have a beam, a complete beam with a complete loading condition, then you don't need to construct the shear force diagram to determine the critical location for the shear force. So V, as usually, is given in the question, if the question was of this type of question, okay? The only thing is Q. We need to understand the mechanism of how we can determine which part of the beam we need to calculate the Q for. So now when I did cut the point at which the question is asking us to determine the shear flow, so I used my knife to cut it at this point. Then I placed a mirror at you could say half, I mean, the shape is identical, so halfway from the left, halfway from the right side. So I placed this mirror to do whatever I did on the left side to be done on the right side automatically. And then this component of the cross section has gone disconnected from the rest of the beam. That means the Q is calculated for this component only. The Q is calculated. And what Q is, we know what Q is. Q is the area of that component times how far it is. You could say Y bar, Y prime, I don't know what you call it, as you like. A times Y, let's say call it bar or prime. It's from the centroid of that element to where the neutral axis is located. So this is what Y prime or bar or whatever you call it, this would be the distance, okay? This would be the distance from the centroid of this shape. So it's easy to know about the centroid of a rectangular shape. So that means from, if the thickness is 10, then half of it would be 5, and then you add the distance from here up to the neutral axis. That should be calculated. That should be calculated, okay? So that's all. That's the mechanism we can. So that for B, we know the mechanism. I think it's clear that, and I am going to do it for the for point, which point left is C. Okay, now for point C, the same thing. I bring my knife. Okay, I need my knife all the time to get this procedure done. This is my knife. Okay, there is what is asking us is to determine the shear flow at B. I did it for C. Okay, for C. So I need to place my mirror again. My mirror, I place it exactly here. Okay, so I have an identical shape on both sides. So now I bring my knife and I cut. Okay, I cut, then the mirror would automatically cut it exactly where did I cut it. I cut it over here, so this will be cut automatically by the mirror on the other side. So what I'm gonna get to determine the Q, I'm gonna get this part would fall. This part is the part that get disconnected from the rest of the beam. This part would get disconnected. So the Q would be my second Q for C. We call it Q for C, okay? Q sub C, okay? Q for sub C would means A of that specific element, the area of that specific times what? Y bar or Y prime, whatever you call it, okay? The distance from the centroid of this element to the neutral axis, centroid to the neutral axis, that would be Y bar, and this would be QC. So once I've got QC, what is shear flow for C? It would be equal to the shear stress, the force that I have it, 850 over moment of inertia for the cross section is calculated, okay, times Q is the difference. So Q is the important element for Q, shear flow for C, and shear flow for B as well. For B, I use the same shear force, okay, which is 850 times the Q is the different one, which is for B, and I mentioned to you which one is for B, is this element, okay, that would fall apart or would disconnected over moment of inertia about the neutral axis, which is the same. Once you calculate the moment of inertia about the neutral axis, this would be the same as exactly as this, same value, the same, everything is the same. V is the same, V is the same, so the only difference is Q and Q. Okay, Q at C and Q at B. Okay, this is Q at B. Okay, this is how we calculate the shear flow. Okay, this is what the yeah.
So Q it's here.
Q is I just now told you mathematically what Q is. If you want to know the name, is moment of area. If you want to know how to calculate it, is the area of this. If are you talking about QC or QB? Which one you want to know? QB or QC?
Or generally, like generally.
Generally,
Q is what area?
Q is the area times how far is it from the neutral axis. How far the
Okay.
element from its centroid to the neutral axis. So the area of that element times how far that element is from the centroid, starting you calculate it from the neutral axis, or sorry, from the centroid of the element to the neutral axis. That's what Q is. V is the shear force, I is the moment of inertia of the neutral axis of the whole composite shape, okay? So this and this would be the same for both sides. The only difference is Q. That's why Q has to be determined with a mechanism. It's not difficult, but it's not easy if nobody tell you how to find it out. A textbook wouldn't tell you bring a knife and cut it over here, then place a mirror, then automatically will be cut on the other side at the exact same point that you have cut at this side, right? So you need to understand this mechanism so that you know which part would represent Q, or which part you're going to calculate the Q for, which part you're going to calculate the Q for, okay? That would be the mechanism for this question. Once you get the shear flow, that would mean if shear flow at B and C is calculated. Let us check the solution. Let me clear up all the mess and then go and see the solution. If there is anything that I missed, I hope I didn't miss anything, hopefully. Okay, move it. QB, Q, okay. Now, one thing that I didn't talk about. If you could see over here is given prime, Q prime, and over here is QC prime. What this prime is about? Okay, the question is telling us determine the shear flow at B and C. That means this point and this point. What I did just now when I calculated for QB and C, I did the right thing. Of course, I did cut B at this location, and the mirror did the same thing on the other side. And for C as well, I did cut here and I did cut here. The shear flow, what you got now of shear flow, which is Q, let me show you, QB prime is called, and QC prime, okay, that we have just now calculated. We said is V times Q B over B, okay, over moment of inertia. Why this prime? Why this prime? What for we have placed this prime? Okay, QC over I moment of inertia about neutral axis. What this prime is about? The shear flow is given to these 2 points. In fact, when you calculated this QB, it's not for this P, it's not for this point. It's for these 2 points. It's been calculated. The same thing, when you calculated this, you have calculated for these 2 points. So what the question is asking for, determine the shear flow at B and C, that must be resisted by the glue. So the question is telling you specifically, I just want to know how much of shear flow I would have at this point. But using this mechanism, you've calculated for these points. So what I'm going to do, what I get of result for QB prime, QB prime, if I divide it by 2, then that would represent the actual QB. That means the shear flow at this point. Why? Because the shear flow is for both sides. If I want only one side, then divide it by 2. So half of it would go to this side, the other half would go to the other side. The same thing for QC prime. For QC prime, if I divide it by 2, okay, that means I'm going to get Q at point C, which is this, only this. So the glue that I'm going to place has to resist that much of shear flow. The glue that I'm going to use to stick this element to this element, or this part of the cross section to this part of the cross section, I need to have a glue of that much of strength, which is equal to QC. So which is equal to half of what I have done of calculation. Half of what I have done of calculation. Why? Because when I did my cut this point, I also did cut at this point, and of course I have 2 points of contact. I have 2 points. It's not a unit. It's not like a board. If you call this as a board, is not a single. This board is independent from these 2 boards. But in case if this was my point and I needed to cut this point to get this part disconnected from the rest of the beam, and in fact there was no glue at this side, then this QB would have been no prime. This QB would have been the real QB at this point. So if the question was like this, I repeat again, this is an important thing that we need to understand. Because the upper side, this flange, I call it flange, okay? This is my flange. The flange is independent from these 2 webs, okay? Because they are glued. This is glued. This part is glued at this point and this point, okay? When I get Q and I do this mechanism, I cut on this side, cut on this side. So the shear flow is calculated automatically for both sides. So to get only for one side, I divide it by 2. That's easily understood. I think you can understand that easily. But if this was not glue, if this board was like an L-shaped board and it's only glued at this point, okay? So how to let me check with the color. I'm gonna aid you to understand. This part is not glued. So I remove the glue. This is a single unit, okay? So it's an L shape. If you look at this, looks like an L shape, okay? L upside down L shape, okay? Okay, it's an L shape this way, L shape this way, right? It's not glued. It's not glued at this point. But when I need to calculate the Q, I do the same mechanism. This mechanism is fixed. I place a mirror at this location. I bring my knife, I cut it over here. I also do cut over here so that I get the element disconnected from the rest of the beam. But what I get of QB prime is not QB prime. It would be QB, the real QB. Why? Because it's only connected at this point. This point is part of, I mean, this is a single unit. It's an L shape. I didn't connect it. There's no glue. There is nothing. It's connected by itself, naturally connected. Okay, it behaves as a single unit. This L is a single unit made of wood. I didn't connect it. There's no glue, no fastener, nothing. So that QB would be the QB for this one only. Okay, so that's what you need to understand. Okay. If you have a question, you could ask. If no, let me check. If you have a question, we move. Okay. If you have a question, you could ask about the mechanism that I use to get Q. That is important. That's one. Why did I divide it by 2? What I got of shear flow. That is important for this question. And the last thing is why we do not need to divide it in case if the member was not glued to this member. Even for this one, if it was like glued on this side only to this side, and it's not glued to the other side, like that means we have another L shape or T shape, you could say. T shape, it would be a T shape. Okay, it's not glued, it's single unit. That means it's originally connected. It's like you have a single piece of wood and it has this shape. Okay, it has this shape. So it would behave as a single block, as a single unit, as a single object. Okay, it's not glued. But this, due to the glue, it would behave as a single unit with this part. Due to the glue, it's not naturally connected. Okay, due to the glue, it's not naturally connected. So it's like you have a joint over here, and this joint is the mean to connect this side to the other side through glue or a rivet or a fastener or anything else. Okay. So if you have a question, please ask. If no, we move. Deniz Bale.
ئوستاز مەبەستەوەیە کە شێر فلۆکە دابەشدوو دەکەین مەبەستەوەیە ئەنجامەکە دابەشدوو دەبی کە دەبینرێتەوە جە دابەشدووی دەکەین.
Bale. Am ئەنجامەی کە دەری ئەەکەی, what you've got of result is divided by 2. What you've got, QB prime is divided by 2. Why I divided? Because the shear flow is calculated for these 2 points. The shear flow is